Hello. I have already discussed. We have already discussed neural network in quite some detail, and then we discussed a little bit on regularization and its implementation in neural networks. Although the regularization, the regulation which we discussed at that time is the L2 regularization. Uh, it is called the L2 regularization, in which we try to reduce the all the theta values. So basically, try to reduce all the theta values using the L2 regularization. What regularization helps us achieve is to reduce overfitting. Okay, now what is overfitting? If you remember, we have already discussed, I believe, what is overfitting and what is underfitting. Okay, especially in the context of linear regression and logistic regression, and here the concept of overfitting is very similar. Only thing is, the way the model is built in neural network is appears to be quite different. In it, we add these neurons. Okay, so suppose these are your suppose here the inputs given here are x1, x2 and x3, and then suppose these are your given suppose this is your neural network which you constructed for predicting certain output y. Okay, certain output y. So this is your x1, x2, x3, these are your input neurons, and you are trying to predict a certain output y. Now you might have, suppose when the input is given to you, there are it might be in a form like this, in a tabular form like this, where you have x1, x2 and x3 given in the tabular form, and in this table you will have a number of rows which are the observations, and of course there will be y output, corresponding output for these inputs. Just a minute. So then you have, so suppose you have only 15 rows given in this data, then, and suppose you have only 15 so these are your 15 sample points, which are given to you, and based on these sample points you want to construct you want to find out the relevant theta values for linking this neural network. Now you have constructed a very large neural network. Suppose you have constructed a very large neural network with a lot of neurons, and these are fully connected layers, so which means that every neuron is connected to every other neuron in this. Okay, every neuron is connected to every other neuron in this network. Um, then suppose you try to train this network. What will happen is, there are theta values connected with every pathway in this network. Okay, so let me try to draw it again in another fashion. So this means that every neuron here is connected to every other neuron. So that means every value here has a theta 01, theta 02, something like theta 0n, then theta, sorry, so this is theta 1 1, theta 1 2, theta 1 3, theta 1 4, theta 1 5, theta 1 6, like this, up to theta 1n. Then you might have theta 2, theta 2 1, theta 2 2, theta 2 3, up to theta 2n. Sorry, theta 3 1, theta 3 2, theta 3 3, up to theta 3n. Here it should have been, um, no, you get the idea. Okay, so there are how many theta values here? So total number, suppose there are 10 values, 10 neurons in the in the first hidden layer. Suppose there are 10 hidden, um, 10 units in the first hidden layer, then total number of theta values which link the first input layer to the theta to the first hidden layer would be 3 into 30, 3 to 10, which is 30. Okay, so in the second layer, suppose there is again another 10 neurons, then you will have 100. So total number of theta linking both these layers will be, theta matrices will be 10 by 10 matrix, and this will have 100 theta values. Similarly, suppose it is 10 to 8 conversion, then 80, and 8 to suppose 4 conversion, um, 8 4 36, and then 4 to 2 conversion, which is 8, and 2 to 1 conversion to 1. So you can see how many theta values, or how many theta values have to be trained in order for us to get from input x1 x2 x3 to the output y. Now to train so many parameters, we need to train, suppose this is of the order of what, this is of the order of, this is 30 100, so this is about 200 to 300 200 values are there. So 200 unknown variables have to be trained, and suppose we just have 15 rows. Okay, so it clearly is very apparent that 15 rows are clearly not very sufficient to train so many parameters, or train so many these weights or theta matrices or theta values. So this should clearly be a case of overfitting. Okay, so if you try to train such a large network with with data which is small in number, or small number of samples, data which is small number of samples, then you will end up with a overfitting. Okay, overfitting means if you train like this, then you will see that the data fits the training set very well, but it will underperform or perform very much worse than the training set on the test set. Okay, so test set performance will be much worse than the training set performance. That is the case of overfitting, where training set is very well, it will fit very well to these 15 data sets, 15 data samples. But if you give any other sample which is not in this data set, it might perform very badly. So this is the case of overfitting. Now what happens in case of underfitting? In underfitting, suppose you have sufficient amount of data, okay, for example, and um, or, but you have modeled the data set in such a way that, model the neural network in such a way that you have very small number of neurons. Okay, so these are the, suppose the data has 100 input. So suppose the data has 100 inputs, x1 x2 x3 up to x100. So these are your, this is your input layer with 100 neurons, 100 input layers inputs. But in the hidden units, you have constructed only a very small neural network with only two neurons in the hidden unit here, and one neuron in the output unit. Then what happens is that this network would try to model everything within this neuron and within this neuron. So this will be, suppose this is theta 0 x0, suppose this is x0, although x0 is typically not from the input. Suppose this is x1, so theta 1 x1, um, theta 1 1 x1, theta 1 2 x2, like this it can go, theta 1 n xn. Similarly we can have, okay, so this can be theta 2 1 x1 up to theta 2 n xn. Okay, so, and then after that there can be just two connections from this, and then you can have the output y. Now what will happen is that the model is trying to the model has a sufficient number of inputs, okay, sufficient number of samples. So suppose there are 10,000 rows in this sample, while suppose you have 100 rows here, 100 inputs, um, like 100 columns in the inputs, and then you have two neurons here. So total number of thetas to be trained is 200, and here total number of theta which has to be trained is only two. So total number of theta is 202 theta values, or 202 weights which has to be trained to get the final output. Now in this case, what will happen is the neural network is very small, okay, and it is trying to find a pattern within the data, uh, which is a large dimensional data, means it has 100 dimensions, while the neurons which are there to try to model this are only two. So the model will have to underfit. it cannot model very complex relationships between the input vectors, or it cannot model very complex relationship between all the dimensions of the input vector, and so this model will tend to underfit. So you have to increase, so there's where the there can be a trade-off. Like if you can increase the, say, number of neurons on this side, and suppose this is your accuracy, or say mean square error accuracy, then on the training set, for a underfit for a data which is, for a model which is underfitting, the model will perform worse. Both, if a model is underfitting, the model will perform worse both on training set as well as test set. Okay, but if a model is overfitting, then the model will perform well. So suppose model, the number of neurons are very small, you're standing somewhere here, your accuracy, let's on this axis, let's have error. So the error will be high both for training as well as test. Okay, so suppose this is training error, and suppose this is test error. So if the number of neurons are very small, you will have both, you will have high error both in terms of training set as well as test set. But if the model, so if you go on increasing the number of neurons, you will see the training performance, the error in the training starts reducing. Okay, and it will keep reducing. Sorry, let's make this reverse, because typically the error on training set is higher than, sorry, error on test set is higher than that of the training set. So I'm putting this one here and this one here. Okay, so initially both training set error and the test set error will be very high, but as you increase the number of neurons and number of layers, that the model, that is the model complexity is increasing, what will happen is the training error will start coming down. Okay, training error will start coming down, and you'll see it will flatten out. Okay, flatten out, or it will never go. If you go on increasing the number of neurons or complexity of the model, what will happen is the model will at some point start overfitting, but overfitting never reduces the, never increases the error. Okay, so if the model is overfitting, the training set will still continue to perform very well. Okay, but when the model as you increase the number of neurons, the test set error will also start coming down, but at a particular point you'll see that test set error will start diverging, because there's where the model starts overfitting, and it starts fitting so well to the training set that it starts um, not to fit very well with the test set. That is, it is learning very specific characteristics of the training data set. That's why it is not fitting very well, or it's not generalizing the overall characteristics of the data. If you are generalizing the overall characteristic data of the data very well, you will be performing almost similarly well in both training and test set. So this is kind of your sweet spot. Okay, where you want to be. So you can increase the number of neurons, increase the number of neurons. When I say that, doesn't mean only increase the number of neurons, it means increasing the number of layers, and increasing the number of neurons. Okay, you can, and this is the hyperparameter optimization. So number of neurons per layer and number of layers, these are both hyperparameters. So you can, hyperparameter means you have to, you can change and experiment, and see in which direction the error is moving as you are changing the number of layers or number of neurons. So in neural network, the problem is the number of hyperparameters increase by many more factors. Like there are many different hyperparameters compared to, say, doing linear regression or doing logistic regression. Okay, so this is how, so when the model is optimal, let's go through this text here. So when the model is optimal, that means it has learned the general characteristic of the data and successfully overlooks the special characteristics of each sample. Okay, so for example, suppose the model is trying to find the, suppose the model is trying to find whether a speech sample is told by a boy is spoken by a male or by a female. Okay, so you give it a lot of speech samples. Okay, and then you give it a label that whether it is by a male or by a female. And then after a while, so you can try modeling with different types of different models of neural networks, and then try to see which model it is performing, what to say, where the test set and training set are both small. Okay, so if the model is overfitting, that means it is trying to look into even what is there in the speech. For example, if some um, uh, while s- while somebody is speaking hello, or somebody is speaking, say, hi, cat, dog, or something, it doesn't matter what is the content of the speech, but what matters is the frequency of the speech, um, because the pitch of females is higher than the males, and the model should learn that. It should only focus on learning the frequency components within the data, within the speech sample, and the not the content. Okay, or the amplitude content of the speech, or even the mild variations in the pitch. It should see what is the central pitch and whether that pitch is falling within the general boundaries of male or female speech. Okay, so if the model is able to learn that parameter, then we say that the model has um, is optimally fit. Otherwise, if it is overfitting, then it might learn very specific characteristics of the data. That was one example. There can be other examples also, depending on what you are working on. Okay, so for example, somebody is working on, say, finding the looking at a skin lesion and trying to predict what kind of lesion it is, or what kinds of skin disease it is. Okay, so the model should look at the structure of the lesion and the disease, and should be able to tell the disease without getting affected by, say, the skin color. For example, a South Indian skin might be much darker than a North Indian skin, or somebody from the African origin versus a Caucasian origin. The skin color might be different, and the model should be able to eliminate that part. Like, it should not, for example, a model is trained only on Caucasian skins, then it might have learned even that into its parameters, that the color of the skin should be light, which should not be the case. So that's why it is many times important that we train the model on variety of data sets, which kind of averages out the underlying variations, which we want the model not to be very sensitive about. Okay, so if you are, say, doing a skin lesion detection model, and you have only trained it on people from, say, Himachal Pradesh, and then you pass it on to a doctor who is practicing in Tamil Nadu, and then the model starts giving a lot more erroneous results, then you should not be surprised, because the model has also learned the specific characteristic, the skin color, which it should not have learned in the first place, and that could have been eliminated by giving it a variety of data sets, both from the north side skin as well as the south side skin colors. Okay, so this is what uh, you know so this is what you can do for eliminating some of the overfitting or underfitting issues. Although the that was something which you could have, that is some normalization which has to be done in terms of how the data or the data quality, that is something which is related to data quality, and that we might discuss later. But overall, if the model this kind of regulation, or this kind of overfitting or underfitting can be is related to amount of data which is available to you versus the complexity of the model which you want to build. Okay, so if the amount of data which is available to you, or number of samples of a data set available to you, is less, that means you should refrain from constructing very large models. Okay, and if you construct very large models, then try to implement Then you have to implement regularization in order to um, either L2 regulation or dropout regulation, which I'll talk after this, to learn the general parameters of the model. If you have sufficient amount of data, okay, a large amount of data or a number of dimensions in the data which you have to learn, then constructing a very small neural network will tend to underfit it. So you need to construct a large so you need to construct larger networks, to and ideally we always want the neural network to be very large, and so that it learns a lot of intricacies of the data. But that can only be possible, such a neural network will only be able to do a generalization of the data if we have a large number of samples available. If you don't have a large number of samples available, then again you will have a large number of samples available, and your neural network is very large, then you will again land up with overfitting. Okay, so you should avoid underfitting and overfitting, and for that you can do hyperparameter optimization, as shown here. Okay, so this is the way of generally doing hyperparameter optimization. So L2 regulation we have already discussed. It tries to minimize all the theta values simultaneously, so that the and I have already discussed in during the regularization discussion of the logistic regression, why reducing the theta values for overall theta values for all the pathways, all the neural pathways, or all the, what to say, all the inputs associated with all the inputs, helps to generalize the model. Okay, so I'll not discuss it again. If you have doubt, you go back to the regulation discussion which we did as part of our we go back to the regulation discussion which we did as part of the logistic regression. Okay, now we come to dropout regulation. It is a very popular method of regulation in neural networks. In this, the idea is, um, now one thing which I don't know if I emphasized enough, but in the lecture in which I have noted it down as a visual introduction to neural networks, in that you can it is very clearly shown like how neural networks work. Neural networks basically try to and these are suppose your inputs. Okay, so these are your x1, x2 dot dot up to xn. So these are your inputs, which are the very, suppose these all inputs came from, say, the MNIST data set, um, which is the image. So these are, suppose, each pixel of this image is suppose going into one of these neurons. So this is the most grainiest information in the data. Okay, but typically the way we perceive images, we don't look at pixels on a person's face and try to identify the person. Okay, we look at very high level features. Okay, we look at complete nose, structure of nose, we look at complete eye, the structure of eye, the color of eye, the structure of hair. Okay, so these are not pixel level information, but these underlying to these are definitely very grainy color and point information. Okay, so what neural network does is that, on the so if it is a fully connected neural network, it takes information from these single neurons and then constructs the one level higher information, okay, in the next layer. Then suppose this layer now only identifies curves, this layer identifies lines, this layer identifies angles. Okay, something of that sort. So if a curve is suppose there is a curve which appears in the image, and there is, suppose the image has a curve and suppose two lines, something like this. Okay, so what will happen is, this neural network which is related to this curve, and this neural network which is related to this side line, and this side L, or 90-degree left right side 90 degree, and this is left side right angle, these both will go high. And then suppose this part is now recognizing something like this. Okay, so then what will happen is, the neurons, the pathways which are connecting this neuron to this, this neuron to this, and this neuron to this. These three pathways, the theta values will become high if such a structure is appearing within the image. Okay, then automatically what will happen is this neuron pathway, uh, these three neuron pathways will go high, which are marked here in green, and they in turn will make this, this neuron go high. And if this neuron is high, then this will then, suppose this neuron will then recognize this pathway. Similarly, there can be other structure. For example, there is, you are looking for a say circle, okay, or you are looking for, let me take, for example, this neuron is recognizing this side, and this neuron is recognizing something like this. So suppose there is some other image here which is supposed to be like this. Then what will happen is this pathway again, this pathway will go high, this pathway will go high, okay, and these two pathways can then come together. Then these two pathways can come together here, and then this together can represent something like you have a house with antenna here or something like that, okay. And so this can recognize whether there is a house with an antenna, or there is house with antenna or not, okay. So you can think about, like, every layer in this network is recognizing, so every layer in this network is recognizing higher and higher level features, okay. So this level, for example, this level is recognizing house and antenna, okay, together. uh, Not exactly this level, actually. This level is recognizing even further. So this level is recognizing house and antenna, this level is recognizing house and antenna separately. Antenna is recognizing here, okay. And this level is recognizing, this level is only recognizing structure, overall shapes like curves, lines, perpendiculars, okay. So this level is recognizing even lower level features, and this level of course is only pixels, okay. So you can see every layer is recognizing higher and higher level features. And so at this point in the layer, at this point in the layer, you can think of, it's almost like, a human brain, okay, which is, and this is, suppose this point is, suppose your eye, okay, this point is your eye, and this point is a very high level neural network in your brain which is recognizing, oh, there is a house with a antenna on side, okay. So you can see, this this structure itself is very representative of the way in which we recognize things, okay. But this was just a digression from the thing which I wanted to really discuss, is that, but it will help us to understand dropout regulation. So dropout regulation is that, suppose you have a very large network, uh, but the amount of data which is available to you is small, okay. So you want to learn, you want to make every neuronal pathway to learn something about the data, okay. What will happen is, if you, um, you know have very less amount of data and you train it to very, and you go on training, what might happen is, based on how much data you have, it might learn very specific characteristic of data along particular pathways, okay. So certain pathways can become very strong. uh, so certain pathways, for example, certain pathways can become very strong, okay, while certain other pathways, while other pathways can be kept weak, okay. So if the data is very small, it can learn, for example, you can show, suppose you are recognizing, making a program which is recognizing houses, Okay, so this is suppose the color pathway of the house. So house has suppose a color. Now the kind of houses which you have in your images, suppose they have all pinkish or reddish color. Okay, so what might happen is that the neural network might just learn the pathway which is related to the color. Okay, it might just learn the pathway which is related to the red color, and whenever you show it a green color house, it might completely reject it, because it has given so much weight to that red color pathway that it recognizes only red color houses as houses. So that's why you want to make it learn the color, as well as you want to make it learn the other pathways, such as the shape of the house, or the number of windows in the house, something of that sort. Okay, so these are different pathways. Even if your data has only pink and red houses, say, you still want it to learn from the other parameters, with some significance attached to them. Okay, rather than so attaching too much significance to the color of the network. So that's where what we can do is we can do dropout regulation, where you have less number of data samples, like number of house images are only limited. Say you have only 50 house images, but all of them have, say, reddish or pinkish or some kind of character which is very similar in all of these 50 houses. Then suppose you want it to learn other parameters as well in equally, or equal relatively equal, what to say, emphasis with other parameters, such as shape of the house, the number of windows of the house, or you name it. Okay, so in that case what we can do is we can suppose this is your neural network. This is your flattened image of the house. Flattened in the house, I hope everybody understands. Like you take the two-dimensional array and convert it to one-dimensional array, just the way we did it for MNIST. So in this case, suppose this is your fully connect. These are your fully connected layers. Fully connected layers means every neuron is connected to every other neuron. In dropout regulation, what we do is for every epoch, in every epoch, all the images are means all the images or all the data points are passed. Okay, so in every epoch, suppose you have now this is having, suppose this is a 4 5 6 7 8 1 2 3 4 5 6 7. Okay, so this is suppose this is having 100 neurons. Okay, that is, there are 100 pixels in the house images, and suppose you have 50 such house images. Then you have, so when you pass in the initial matrix, you pass in um, what number of rows is 50 into 100. You pass in 50 rows of 100 pixels, and sorry, you pass 100 rows, sorry, you pass 100 what to say, columns, 100 columns, 50 rows. You pass 50 rows, 100 columns. Each column represents one pixel of the house, and then this is passed on to the next layer, to the next layer, to the next layer, to the next layer. Okay, and this is all multiplied and added, multiplied and added, okay, in the matrix forms. And finally you have a forward propagation. So this is your forward propagation, forward prop, and then you have your back prop. Then after you have done your forward prop, you have a given y, that whether it is a house or not house, you compare the output a n with your given y, and then you start doing a back prop. Okay, so this is again multiplication and additions in series, and then you get back and you try to do the dj by d theta, um, d theta n, for d theta n for every layer. Okay, and you try to do theta n equal to theta n minus g theta n. Okay, so these are all matrix subtractions. The same thing was implemented if you go back to the assignment of neural network from scratch. Okay, and then you'll see here. Okay, this is your assignment number 7. In this you can see we took the x matrix, which is the complete 60,000 multiplied by 700 something, right? So you have 728 numbers and so 60,000 such numbers. Okay, 728 is your 728 or something like that. 28 into 28. 28 into 28 and 60,000. Okay, so this is the number of elements or number of samples of the handwriting images which are passed on, and then we go through a forward prop and then a backward prop. I'll not explain it again. You can go through it to see how this works. Okay, so in this case, what is happening is every theta is getting trained for every forward prop and every backward prop. So in dropout regulation, what you do is during so in every iteration, all the inputs are passed. Okay, in every iteration, all the inputs are passed to the end and then back. Okay, in dropout regulation what we do is we drop out certain, so we give a dropout factor. Okay, so say we give a dropout factor of 0.2 to this layer, 0.5 to this layer. So that means during the forward prop, during one epoch, okay, what we write as epochs. Okay, during one epoch, um, rand will select 20% of this. Okay, 20% of neurons in the first layer here. So here we have 1 2 3 4 5 6 7 8 8 20% of 8 is little, so let's make it say 10%. Okay, so 10% of neurons, 10% of neurons is zero point 0.8, um, 80% of 8, say we take zero point 0.5 here. Okay, 0.5. So that means 50% of the neurons will be selected randomly and will be eliminated out of the pathway. How it will be eliminated out of the pathway? It's basically we set the output here as 0. We set the outputs here as 0. So that will automatically ensure that the next layer these outputs are not passed. Suppose um, here again, suppose you set 0.3 or something, and suppose that means only two of these are eliminated. So we eliminate two from this pathway. Suppose this is again 0.25, then only one is eliminated. So during one forward prop, we randomly select certain neurons and set their output to 0. Okay, so in the next iteration or in the next epoch, we'll again choose randomly some other neurons, not exactly this will be randomly selected again in the next epoch, and some other neurons will be eliminated in the next epoch. Similarly, some other neurons will be eliminated in the next epoch. Okay, similarly here some other neurons will be eliminated, some other neurons will be eliminated in the next epoch. You keep doing this, you keep cycling through this, for every epoch you change the number neurons randomly, or you throw out certain neurons randomly, and keep doing the iteration in this way. This will ensure that no particular pathway is favored over the other pathways. Okay, for repeated training. So even if there is a certain character in the data which is unnaturally overemphasized, especially due to the characteristics or the way in which the data was collected, that might be suppressed through this method. Okay, and it has been seen that the dropout regulation performs just almost as well as L2 regulation. Um, and so the way dropout regulation has to be implemented in the program in TensorFlow, I'll show you an example which I have just modified the previous code which I had. So this is your This code I had shared in the lecture number 16. In the lecture number 16, this code was there. I'm just modifying that same code here. After every dense, I have added a another import here from the keras, which is dropout. Okay, so from tensorflow.keras.layers, I was earlier importing dense input and activation. Now I'm also importing dropout. Now how to implement dropout is that after every layer, so this part of the code was already there. Okay, this part of the code was already there. After that I have added a dropout layer. So in this dropout layer, I'm just writing x equal to dropout 0.2x. That means 20% of the outputs of the previous layer will be dropped out. Okay, for and this will be dropped out randomly for every different every epoch. Similarly, for the next layer, I have put 0.5, like 50% dropout, and after that, I have not put dropouts. You can choose in which layers you want to put dropouts, and for every layer, how much percentage dropout you want to put. But implement dropout only if you have overfitting. Okay, if you don't have overfitting, you have sufficient data to train the model size which you are planning for, then that's fine. You need not implement dropout, it's an optional step. But if your model is very large, or you want to train a very large model on a data set which you believe is smaller as compared to the parameters which you have to train in the model, then it's a good idea to implement dropout. Okay, so that way you'll be reducing your overfitting. How can you check? Now this is another command which I forgot to mention last time. You can add a dot summary to your model, and then it will show you the summary of the model. Okay, so what is the first layer to second layer connections, and where are the dropout layers. This is all, and how many parameters are there total in the model, like how many theta values. It's 84,780. Okay, so which is comparable to the 60,000 rows which you have. But if you say increase it by double or something, still dropout is a good idea to it's good idea to add dropout if your model size is almost hitting, the total number of parameters is almost hitting your input sample size. Or if your total number of parameters is 10 times 20 times more than your sample size, dropout is definitely has to be implemented. And then where dropout will help you to what dropout will help you to see is, if your accuracy, your training accuracy here is much higher than your validation accuracy. Okay, then that means you are performing, you are performing much better than in your training set than your here the validation set. Ideally your training set accuracy should be very close to your validation accuracy set. um, and both of them should be performing very well. If both of them are performing very performing worse, like your accuracy is the training set accuracy and the validation accuracy which is the test set accuracy here, both of them are say 50%, that means you are performing worse in both of those cases. So that means you are underfitting. If both of them are, if training set accuracy is performing much higher than the test set accuracy, that means you are overfitting. Okay, so this is what you have to take care of. So this is all I wanted to discuss today, uh, and I will come back to you with another lecture soon. Thank you.